It's exam 1 from spring 23. First, configure this configuration of charges, and I want you to sketch the E field vectors at point A. So due to the 9 nanocoulomb charge, there's going to be an electric field vector that's in this direction. I'll call this one E1. And then due to this negative charge, there will be a bigger E field vector, and I'll call that E2. Let's go ahead and get our angles right. So notice this is a 9, 12. So this leg of the triangle is 9 meters, 12 meters. So that means that this leg of the triangle is 15 meters, right? This is just a scaled up version of the 3, 4, 5 triangle. This angle right here is what, 37 degrees. I can do the inverse tan, by the way, of opposite over adjacent 9 over 12 gives me 37 degrees, which means that this angle is 53 degrees, and that's the angle that I want. So thus sketching the E-field vectors, that's part A. I have the angles shown, I have the vectors shown. Now I want to show your work for calculating the x and y components of those vectors. So first we need to calculate what is E1. That's kq over r squared, 9 times 10 to the 9th. Q here was 9 nanocoulombs, 9 times 10 to the minus 9, divided by the distance, which was 9 meters squared. So I got a bunch of 9s. So that's just equal to 1 Newton per Coulomb. That cancels with that and that. And then E2 is also kq over r squared, but a different q and different r. So E2 is due to this 75 nanocoulomb charge. So that's 9 times 10 to the 9th. 75 times 10 to the minus 9 divided by 15 squared. So those cancel out. That's going to be 3 newtons per coulomb. I think I did that right. So this is the same as 15 times 5, and that gets rid of one of those 15s, and then this is 3 times 3. So yeah, there's 3 nanocoulomb, 3 newtons per coulomb is E2. So now I have the magnitudes of those two vectors. I just need to figure out what are E2x and E2y. E2x is going to be 3 times the cosine of 53. Let's go ahead and draw these vectors over here actually. So I have E1, that's my 1 Newton per Coulomb, and then E2, that's my 3 Newtons per Coulomb, and this is an angle of 53 degrees. So that's 3 cosine of 53. It's equal to 1.8 Newtons per Coulomb, and then E2y is 3 sine of 53. I get 2.4 newtons per coulomb. So those are the x and y components. So now if I redraw that, I have 1 Newton per coulomb here. Over here I have 1.8 newtons per coulomb. Notice it is in the negative direction because I've drawn my vectors, and I know here I didn't have a negative right here on this 1.8, even though it is in the negative direction. Because when I calculate my electric field, I'm only calculating the magnitude of the electric fields, and then the direction of those fields comes into play when I'm actually determining, up here the direction of the electric field vectors. And then my y component is in the negative y direction, so that is 2.4 newtons per coulomb. All right, so that's part B, and now part C. Show my work to show the magnitude of the electric field. I'll do it over here. So first I want to combine my electric field components. So I have 1 minus 1.8. That's equal to negative 0.8 newtons per coulomb. So my x component over here is 0.8 newtons per coulomb, and down here it's 2.4 newtons per coulomb. My resultant vector is going to be in that direction. To find the magnitude of that, I say the square root of 0.8 squared plus 2.4 squared, and I get I get 2.5. So that's the answer for the magnitude. And then I want to find the direction. And notice I want to find the angle counterclockwise from the positive x-axis. So that is this angle, but in order to find that angle, I first have to find this angle. I'll call it the angle phi. So phi is the inverse tan of opposite over adjacent. That would be 2.4 over zero point 0.8. Not putting signs in there. I get 71 degrees. That makes sense. 71 degrees, that's below the negative x-axis, but I wanted it expressed from the positive x-axis. So the angle, I'll call this theta, is going to be 180 degrees plus the angle phi, which is going to be 251 degrees from the plus x-axis. That's the resultant, or the direction of that vector. That was part D. And then finally, in part E, I wanted to know the potential of those two charges. The potential, remember, is the sum of the individual potentials for each individual charge. I have that 9 nanocoulomb and the 75 nanocoulomb. So that's going to be kq over r, 9 times 10 to the ninth, times 9 times 10 to the minus 9, divided by the distance, which is just 9 meters. That's the first one. And then the second one is 9 times 10 to the ninth times negative 75 times 10 to the minus 9 divided by the distance, which is 15. So I can cancel out that, and then that cancels with that. That just leaves me with 9 volts plus that cancels with that. That cancels with that and leaves a 5. So I get 9 times negative 5. There should be some parentheses there. 9 times negative 5, which is what? Negative 45. So I get negative 36 volts. So that's the answer there. All right. In parts A and B, I was looking for the answers, the X and the Y components. Oh, actually, for part B, I wanted to see these as the final answers, the X and Y components. But I was looking for your work too. And then in part A, I was looking for this vector diagram. Okay. Sketch these electric field lines. Because they're both negative, the field lines are going to be coming out like this. And it's important too that since, excuse me, not coming out, that the field lines are going to be going in, and then also recognize I should have twice as many field lines coming in there. And then if I'm drawing the potential lines, they'll look something like this. They actually sort of flatten out as they go out into space. All right, and then I have an electron, just remembering that an electron has a charge of 1.6 times 10 to the minus 19 coulombs, and then also the mass of an electron is 9.11 times 10 to the minus 31 kilograms. So let's just remember that as we're going through this, that's all wrapped up in that word. It's moving from a potential of 6 volts to minus 3 volts. That means that the change in potential is going to be a total of a 9, or has a magnitude of a total of 9.0 volts. Or really, it's going to be equal to a negative 9 volts because I'm going from 6 to negative 3, so I'm going from negative 3 minus 6, or a delta V of 9 volts. Anyway, and then my distance, my delta x, is equal to 0.3 meters. And I know the electric field is in this region is constant. I see that it's moving from high to low potential. This is my high potential. That's my low potential. My electric field is going in that direction. So actually, hold on just a second. Okay, I have a mistake in this. I just want to make sure you get this, and I'm going to change it a little bit. I'm going to make this position A and this position B because an electron, you know, will move in this direction. It's going to move from low potential to high potential. That means that my change in potential is going to be positive 9 volts. That's not going to be terribly important for what we're doing, but it's important to be correct. So my change in potential is going to be a positive 9 volts. So that electron will gain energy as it moves from low potential to high potential. All right, so I want to know first, what is the speed of the electron? So I know that my change in potential is equal to my change in potential energy over Q. That is what my change in, that's how I've defined my potential, that it's delta PE over Q. So that means that my change in potential are that means that my change in potential, I can rewrite this and say that it's equal to the negative of the change in kinetic energy over Q, right? Because if I have a positive change in my potential energy, I have the opposite change in my kinetic energy. So then my kinetic energy is going to be equal to negative Q delta V. So that means that it's going to be equal to negative times the charge of my electron, which is negative 1.6, that should be a negative up there, times 10 to the minus 19 coulombs, times delta V, which I already know is 9 volts. So that means that I have a kinetic energy of 1.44 times 10 to the minus 18 joules. And so I'm going to set that equal to 1.4 times 10 to the minus 18 joules equal to 1 half mv squared, where m is 9.11 times 10 to the minus 31 v squared. I'm going to solve this for v. I'm going to pause here for just a second. So when I do this calculation, I get that V is equal to 1.8 times 10 to the 6th meters per second. So that is the speed of my electron. And then finally, if I want to know the um, the electric field, I know that the electric field is related to the change in potential in this way, that it's equal to minus Ex delta X. So since I have this change in potential moving from A to B, that my electric field then Ex Ex is equal to negative delta V over delta X, which is going to be negative of my delta V, which is a positive 9 volts, divided by my distance, which is 0.30 meters. Now, I'm going to be careful of my signs here because this delta x is actually to the left, so that's going to be a negative 0.3 meters. So I get 9 divided by 0.3 is equal to 30 newtons per coulomb. And notice those signs cancel out. I'm going to make some corrections here. I'm going to list on the figure that this is negative. I'll change the A's and the B's, but be careful with your signs. I'm not going to be a huge stickler for signs as long as you've done it correctly, but notice here that my kinetic energy, my change in kinetic energy is negative. That gives me a positive speed or positive velocity as I would expect, and then also that my electric field is positive as it's drawn in the figure. Okay, let's look at multiple choice. What is the magnitude of charge on a proton? Let's say we just had that. It's fundamental unit of charge. Negative charge is brought near to a neutral conductor. The conductor part is important. And when that happens, it's going to send the electrons over here, and that leaves an excess of positive charges over here. So A is the right answer. Which of these statements is true? A conductor has more protons than electrons. Not true. Could be true, not necessarily. No, not true. An insulator cannot become polarized. That's not true either, that I can have an insulator where it doesn't have any or very few conduction electrons, but that the atoms will orient themselves in response to outside charges. Conduction electrons are tightly bound to the atom. Not true. Charges are evenly distributed on the surface of an insulator. Um, Not necessarily true. All right. So that is the answer is E. I know you might have thought that number 4 could be true, and it could be true in some cases where I deposit, say, negative charges onto an insulator and they stay there. Um, or that you can have an insulator with charges that are evenly distributed. You can really have either way, but it's not necessarily true. And besides, there are no options that are 4 only, so you would determine that that is not a true statement. At least it's not always true. If you touch a doorknob and receive an electrical shock, what has happened? You've had a transfer of electrons. See, I'm going to take out E. E is sort of correct, so number 4, I'll take out E. What is the direction of the force acting on Q1? Well, let's see, the force acting on this charge is up and in this direction. This angle right here in this 3, 4, 5 is 37 degrees, so this angle is 53 degrees above the positive x-axis. Let's just step back on this angle. Notice I have this 3, 4, 5 triangle. I'm going to redraw it. Let's see, I have 3, 4, 5. I want to know what this angle is, or really I want to know what its complementary angle is. I want to know what this angle is. But theta is the inverse tan of opposite over adjacent. That's 3 over 4, and that's equal to 37 degrees. And then I say 90 minus 37, and that gives me 53 degrees. Two charges experience an electric force of 12 newtons. What if you double one of the charges and move it to 3 times their original distance? Let's write Coulomb's law. If I double one of the charges and triple the distance, that gives me a 2 over a 9 and 2 over a 9. Well, what is 2 over 9 times the original force, which was 12? Let's see, so that's 4, and that becomes a 3. So I get 8 over 3. 8 over 3, that's 2.7. So these two charges, the x is equidistant. Where can you place a charge, either positive or negative, on the dashed line where the net force on that charge is 0 newtons? Let's just imagine if I place it in the middle here somewhere, I have a force due to this charge that's in that direction, and a force due to this charge that's in that direction. So I can't have it anywhere in the middle. So it gets rid of those. It's either to the left, a plus q, or to the right, a minus 4q. And in general, you want to get far away from those big charges. So I'll probably assume that the answer is B, but let's just draw some sample vectors over here. The vector due to that plus q charge is going to be in that direction, and the vector due to the minus 4q charge is in that direction. Now, the minus 4q charge is bigger than the plus q charge, but I'm farther away from it too. So there is a place where I can get a net force equal to 0. What is the magnitude of the net force on Q2? So I have two forces. I'm going to call this F1. It's due to Q1, and this one is F3. I'll call that F3. It's due to Q3. F1 is equal to 9 times 10 to the ninth times 4 times 10 to the minus 4, 2 times 10 to the minus 5, divided by 2 squared. So I get some cancellations here, and that's equal to 18 newtons. And then F2 is 9 times 10 to the ninth, 2 times 10 to the minus 5, 8 times 10 to the minus 4, and the distance is 4 meters squared. So that cancels there, and this 2 times 8 cancels with the 16, and that just equals to 9 newtons. So I have F1 is equal to 18, and what I call this F3 right here is equal to 9. 18 minus 9 is 9 newtons. So E is number 8. So there's configuration of charges, which vector represents the force vector acting on the upper right plus Q charge. All right, so here let's draw the vector due to this charge. It's going to be up and in this direction. Let's write that Newton's Coulomb, or Coulomb's law again. Now this charge is twice this charge, so I'm going to put a factor of 2, and this distance is twice that distance. So I have a 2 over 4, or 1/2. That means that this force is going to be half the length of this vector. That means that B is the right answer. All right. You're sitting a certain distance from a point charge. You have the distance. What is the new electric field that you measure? Remember, electric field is kq over r squared. If I have this distance, that's half squared, which is the same as 1/4. That means I have 1 over 1/4 over here, or 4. So I have a 4 times the electric field. All right, electric field is a force per unit charge. It's in newtons per coulomb. Um, Two charges are arranged in this figure. Where is the electric field of these two charges equal to 0? All right, so I like these problems, but they're tricky. So remember here in the middle, I'm just going to draw some electric field vectors. Due to this charge, it's in this direction. Due to this charge, it's bigger and in this direction. So there is a place somewhere in the middle where I can arrange these so that the electric field is 0. But over here, if I draw my vectors, they're both to the left, and over here, my vectors are both to the right. So anywhere to the right of plus q is not going to work, and anywhere to the left of plus 4q. It has to be either B or E. Now, remember how we were talking about how that in those cases, you want to get as far away from the from the big charge as possible. So I'm going to venture a guess that it has to be right here. That is 1 meter to the left of the plus q charge, because I'm trying to get away from that big charge. And the other option, E, is right here, and that's just not going to work because that means that the big charge is going to dominate the electric field. So let's just think about this. I have this distance. If this is the answer, then I have this distance is 1 meter, and this distance is 2 meters. And then we'll draw our electric field vector. So first, I'm going to draw my electric field vector to this charge. It's in that direction. And then I have E equal kq over r squared. 4q is 4 times the original charge, and 2 meters is twice the original distance. So that means I have a 4 over 4, so I have a 1. That means that, well, that electric field is going to be the same, that electric field will be equal but opposite. So I am right in that initial assumption that it has to be the one that's closer to the plus q charge. So B is the right answer for number 12. Now there is a more difficult way that you can do this where you're actually putting in a variable for x, but it gets kind of complicated. It's always better to um, get rid of the answers that don't make any sense at all. And that was the first step that we did. And then the next step was to look at the two remaining answers and say, well, which one of these makes sense? And if you take that approach, then you'll come up with the right answer pretty easily and pretty quickly if you understand how electric fields work. All right, where's the electric field equal to 0? Well, let's just draw some vectors. So I know it can't be D because the electric field, let's see, I'll just go through and, yeah, the electric field due to there is in that direction, and the electric field due to that one is in that direction. So D can't be the answer. How about B? Does that work? Well, the electric field due to this charge is in this direction, and the electric field due to this charge is smaller and in that direction. Those two vectors don't cancel out. The electric field at A, let's see, I have the electric field due to theirs in that direction. The electric field there is smaller, so it's very similar to B, and that doesn't give me a 0 vector. Let's see, C, the electric field in this direction due to that charge, and here it's in this direction. Those two vectors don't give me a zero electric field, so the answer is E for that one. All right, Q1 has a magnitude of 12 coulombs. What is the sign and magnitude of Q3? Well, first of all, I know that it has to be negative, so I can get rid of that answer. I know also that, this has 1, 2, 3, 4 lines, but this one has 6, so it has to be more than 12, so I can get rid of those. Now, I can do a ratio. 12 to 3 means that it's like each of these lines is equivalent to 4 coulombs. I did 12 divided by 3. 12 coulombs divided by divided by 4. And so 12 divided by 4, that means that each line is 3 coulombs. All right, 3 coulombs, that's 4, 3, 6, 9, 12. If there are 6 lines, that means that this has to be 18 coulombs, or negative 18 coulombs. That's probably the best way to approach that. The units of the electric field, okay, that's true, and that's true, so that's the right answer. I have a charged particle. What will the charge do? It's a positive particle. Positive particles will move from high to low. And then also remember that my electric field runs in this direction too. This is my positive side, that's my negative side. Which of these is the potential zero? Okay, so I'm looking along this line. Where's the potential 0? I want a situation so that equal and opposite charges are the same distance. But notice here I don't have any equal and opposite charges. Here, the equal and opposite charges are different distances. And then here, likewise, they're different distances. So none of these. D is the right answer for number 17. All right, here I have 3 charges. I want the potential at point A to be 0. So what must Q1 be? Well, first let's just figure out what is the potential due to these others. So this is 3 meters, this is 4 meters, and this is going to be 5 meters. I have a potential up here of 9 times 10 to the ninth, 16 times 10 to the minus 9, divided by uh, R, which is 4. That's equal to 36 volts. Here I have 9 times 10 to the ninth, uh, 3 times 10 to the minus 9, divided by 3. That's equal to 9 volts. So I need, actually, yeah, this is negative 9. That means that I need the potential due to charge 1 to equal to negative 27 volts. Because 36 minus 9 is equal to 27 volts. That's the combined volts of these two. And so I need this charge to negate those, to be the opposite of those. So I say negative 27 is equal to 9 times 10 to the ninth times Q1 divided by 5. 5. Yeah, that's right. Okay. So let's see. If I solve that, then I find that that Q1 is equal to negative 15 nanocoulombs. So C is the right answer. These charges are all equidistant from one another. Which statement best describes the electric potential energy of that configuration of charges? Well, remember the electric potential energy, U or PE, is equal to KQQ over R. They're all equidistant from one another, so I can just really consider that the product of the charges as a relative value of the potential energy. So I'd get 8, negative 8, and negative 4. That's not actually a measure of the potential energy, like the units are not right, but it gives me the relative values. So I'm just trying to figure out the sign of the energy. So I have negative 12 and 8, so it's going to be a negative potential energy because the sum of these three numbers is equal to a negative value. And then finally, number 20, a 2 Coulomb charge is stationary at point A. It is released. How much energy does it gain when it reaches point B? So I have a Coulomb charge. It's going to move from this point to this point. Notice that the change in potential of that it undergoes a change of potential of 18 volts. And I know that a volt is an energy per charge. So if I want to know its energy, it's going to be equal to Q delta V. So I have a 2 Coulomb charge times delta V, which is 18 volts. So that's 36 joules is that answer. All right. Tough test, y'all. Good job.